Okay, so we're in section 4.3 today, or this video. Area and definite integrals, so we have three things to talk about. The first is we need to talk about how to find area under a curve. And then we're going to talk about evaluating definite integrals and the fundamental theorem of calculus. Theorem of calculus. And we're going to look at some application problems. So in 4.2, we looked at the area under the curve, calculating it using a definite integral. Now, if we think of the area as a function, because as that area changes, as our curve moves from left to right across that x-axis, the area will change. And so we consider that its own function a of x. And we can then link the two major concepts of calculus, derivatives and antiderivatives. So we know our area under our curve is the integral from a to b of f of x dx. And so we're going to see this as a of x evaluated from a to b. And remember, this is the area under f, well, let's say on the closed interval a to b. So now, if we take the integral, the indefinite integral, f of x dx, we know from 4.2 that this a of x is the antiderivative, and our limits of integration are what tell us how to evaluate. So this should just be capital A of x plus some constant c, the constant of integration. And so if we take the derivative of both of these, d dx on the whole thing, this becomes, so we're going to ignore the left side for now, but this is d dx times the integral of f of x dx should equal d dx of a of x plus c. And we know that this derivative is just going to be a prime. And we know, rewriting this, d dx of f of x dx, so this equals a prime. And we know from 4.1 that this a of x is the antiderivative of f. And so that means the area function, a of x, is the antiderivative. And while we may have already guessed at that, the big takeaway here is that when you take the derivative after you've integrated, you get our original f of x. Because if the antiderivative of f of x is a of x, then the derivative of a of x should go backwards. We should undo, and we should be left with f of x. And so that gives us a really important result, that derivatives and integrals undo themselves. They are operational inverses, the same way that addition and subtraction can undo each other, multiplication and division can undo each other. And this representation is what the fundamental theorem of calculus is all about. It says the integral from a to b of f of x dx equals a of x evaluated from a to b, which is a of b minus a of a, and this gives the exact area. Under f on a to b. Now this isn't the only part of the fundamental theorem. There is a second part that we'll discuss, and that is this part here. But for now, let's just use this. So if it says find the area under a graph, like in this next example, we know that we're setting up the integral from -1 to 2 of x squared plus 1 dx. So this equals, first we take the antiderivative, x cubed over 3 plus x, evaluated from -1 to 2, which equals 2 cubed over 3 plus 2 minus 1 cubed over 3, or I'm sorry, -1 cubed over 3 plus -1. And when you add all this up and subtract, you get 6. So we can evaluate definite integrals and know that this is the area under this function, x squared plus 1, from -1 to 2. All right, so another example, this is an e, in case it's not obvious. So our antiderivative of 1 is x, of 2x is x squared, of -x to the -1, that's the same as 1 over x, and we know that that antiderivative is ln. So the integral of 1 over x dx equals ln of x. So this is going to be -ln x. That's the values. And all of this is going to get evaluated from 1 to e. So this is e plus e squared minus ln of e minus 1 plus 1 squared minus ln 1. And again, once we add all these up, ln of e is 1, ln of 1 is 0. We end up with e plus e squared minus 3. And since e is transcendental, we're going to leave it like that instead of writing its decimal, because we don't need to. We want to be exact. Okay. So a little word problem here. Let y equal x cubed represent the number of kilowatts generated by a new power plant each day, x days after going online. Find the area under the graph of y equals x cubed over the interval 0 to 5 and interpret the significance of the area. So we can kind of ignore everything at first and just look at this sentence, find the area under y equals x cubed. So this is, and it's from 0 to 5, x cubed dx. Well, the antiderivative is x to the 4th over 4, evaluated from 0 to 5. 5 to the 4th over 4 minus 0 over 4. Technically, you could write that 0 to the 4th. But this is going to be 625 over 4, which is 156.25. So now that we have that area, we want to interpret. So since our original function y represented kilowatts generated each day, x days after going online, the area that we just found, 156.25, this is kilowatts are generated over the course of, so 0 would be no days, 5 would be the 5th day, so this would be of the first 5 days. And so that's how we can interpret an area that we calculate. If it represents a certain value, then it tracks the total amount that's ticking up across whatever interval I have. In this case, 0 to 5 days, over the first 5 days. So these next three are just some practice problems to get you used to evaluating more integrals. So I recommend you pause the video and try these out. So I'm going to walk through the solutions now. So the antiderivative of x squared is x cubed over 3. This is getting evaluated from a to b. So this is b cubed over 3 minus a cubed over 3. Or we could write it all as one fraction, b cubed minus a cubed over 3. And that would be our final answer. And the next one, the antiderivative of x squared minus x is x cubed over 3 minus x squared over 2. This is getting evaluated from -1 to 4. So this is 4 cubed over 3 minus 4 squared over 2 minus -1 cubed over 3 minus -1 squared over 2. And when you add all that up, you get 85 over 6 as our final area under that curve. And then finally, the antiderivative of e to the x is e to the x, evaluated from 0 to 3. So this is e cubed minus e to the 0, or just e cubed minus 1. And again, it's e, so we're going to leave it as e. So if you didn't get these same answers, double check your algebra first, and then go back and see if you made a mistake in your, actually do that the opposite way. Check that your antiderivatives are correct. And if they're not, see if you can figure out what error you made. And if they are correct, then double check your algebra and make sure you have the correct algebra. Okay, so let's look at another application question. So suppose that y is the profit per mile traveled and x is the number of miles traveled in thousands. We're going to find the area under y equals 1 over x over the interval 1 to 4 and interpret its significance. So again, we can kind of ignore everything except for this last sentence for now. Find the area under this curve on this interval. So that's the integral from 1 to 4 of 1 over x dx. This is ln x from 1 to 4. So this is ln 4 minus ln 1, which is ln 4 minus 0, which is just ln 4. And this comes out to be approximately 1.386. And the reason we want that is because we need to interpret this number. So we're going back to what this is. So y is the profit in thousands, that it's profit per mile, and x is the number of miles. So total profit when 3,000 miles are traveled So y is per mile, so our profit is about $1,386 per thousand. Because these, my point here was that both are in thousands in this question. So we get the 3,000 miles because there's 3 miles or 3 between 1 and 4. And since this is in thousands, 3,000 miles. And then the profit is $1,386, approximately. Obviously, the exact profit is ln 4 times 1,000. So let's talk about finding the definite integral of functions that are non-negative over any given interval. So we can compare these two values, or these two functions, y equals x squared and y equals negative x squared, from 0 to 1. So we're going to consider 1 and 2 here. Now, the graphs of the function, they do basically the same thing, but if we were to integrate number 1, this would be the integral from 0 to 2 of x squared dx, or x cubed over 3 from 0 to 2, and this is going to equal 8/3. However, over here, if we do the area, this is again from 0 to 2. It's negative x squared dx now, which would be negative x cubed over 3 from 0 to 2, and this equals negative 8/3. So it makes sense that our area should be the same, because as this little paragraph says, x squared and negative x squared, they're just reflections of each other across the x-axis. And so what this is supposed to do is to show you that negative valued functions, the definite integral gives us the opposite area between the curve and the x-axis. So you get negative areas when you're below the x-axis, and you get positive areas when you have a function above the x-axis. So now if we consider x squared minus 1, which looks like this, and we try to integrate from 0 to 2, notice we have something above and something below. So what we want to do is at this point right here, where it crosses, we split the region. So we have two areas then. We have the first integral, which goes from 0 to 1 of f of x dx, and then we add that from 1 to 2 of f of x dx. And so this is a big property of definite integrals, which is what this next box is. Don't know why the symbol is messed up, but this should be the integration symbol on all three of these. So the integral from a to c of f of x dx is equal to the integral from a to b of f of x dx plus the integral from b to c of f of x dx. And again, this hinges on the fact that b is strictly in between a and c. So a lot of times you will have an integral, or we'll use the other one as an example, the one we just have up here. If we did x squared minus 1 dx this way, this would be x cubed over 3 minus x from 0 to 2, which would give us 8/3 minus 2, which would give us 2/3. And if we do it the other way and we split it like this, we have the integral from 0 to 1, x squared minus 1 dx, plus the integral from 1 to 2, x squared minus 1 dx. And this is going to equal x cubed over 3 minus x, evaluated from 0 to 1, plus x cubed over 3 minus x, evaluated from 1 to 2. And what we get here is 1/3 minus 1 plus 8/3 minus 2. And then minus 1/3 minus 1. So the 1/3 minus the 1/3 will cancel, the -1 minus the -1 will cancel, and we're left with 8/3 minus 2, which again is going to give us 2/3. So I choose this particular problem on purpose to show you that when you have a continuous function like this, you can do the interval no problem, the integral no problem over that interval. And if you split it and you don't split it, you will get the right answer. So what we want to do is make sure that when we don't have a continuous function, that we split properly, and we're not doing too much of one side of the interval or the other. And you'll see what I mean in a couple examples in a bit. So this process, oh, I gave us space to do that here. This was just supposed to be for the second interval. So this process is finding net area. And as I said, the definite integral of a continuous function over an interval is the sum of the different pieces, splitting it, and it's called net area. So sometimes your net area can be positive, sometimes it can be negative. It all depends on what is higher, the thing that's above, or what value is higher, the area above the x-axis or the area below the x-axis. So in this next one, we're going to be using something like this for profit. So determining total profit from marginal profit. So the airlines determine that the marginal profit resulting from the sale of X seats on a jet traveling from Atlanta to Kansas City in hundreds of dollars is P prime of X equals rad X minus 6. So find the total profit when 60 seats are sold. So total profit, that's area under a curve, total. So it's going to be 0 to 60. P prime of X dx, because we know that P prime is the marginal profit, so the antiderivative will be the profit. So this is the integral from 0 to 60 of square root x minus 6 dx. This is the integral from 0 to 60 of x to the 1/2 minus 6 dx. So we're using a power rule for integration. So this becomes x to the 3/2 over 3/2. Whoops, not this yet. Minus 6x, and then evaluated from 0 to 60. So this is 2/3 x to the 3/2 minus 6x from 0 to 60. So plug in the 60 first. 2/3 times 60 to the 3/2 minus 6 times 60, and then all of this minus plugging in the 0, which is 0 minus 0. And when we punch this into our calculator, we get at negative 50.1613. Now remember, this is in hundreds of dollars, marginal profit is, or our profit is. And so this means that when we only sell 60 seats, the airline is losing, it's hundreds, so multiply by 100, 5,016.13 cents, and this is dollars. And they're losing that. So now think about this in the airline. How often do you hear when you fly people saying, or the airline saying, we have a free seat, or we want to do this? Here's a better question. How many times have you been on a plane that's been overbooked? They booked too many. Well, this is why. Because they want to make sure that they sell as many seats as possible to hit that point where they're no longer losing money. Now, once they hit that, usually it goes up fast. So the airlines start making money a lot more once they match this threshold. Right? On a big commercial airliner, you could have hundreds of people on the plane. So our last couple examples here, all about velocity, distance, and acceleration. So this is just a little refresher. Remember, s prime of t is the derivative of your position s, and that's our velocity function. S double prime is the derivative second derivative of s, or the first derivative of v prime, and that's our acceleration. So we can use this to solve problems when we want to find position from acceleration. So example, suppose that v of t is 5t to the fourth, s of 0 is 9. We want to find s of t, and we're going to assume this is in feet and velocity is feet per second. So v of t equals s prime of t, which is 5t to the fourth. So that means we're going to take the integral from, well, we don't know. So it's going to be indefinite, 5t to the fourth dt. The reason we leave it indefinite is because we want to find s of t. If we made it a definite integral, we would just find a value. So our antiderivative here is t to the fifth plus c. So our guess for the position function or the distance function is t to the fifth plus c. And then we use our initial condition. This is an initial value problem. S of 0 equals 0 to the fifth plus c, and this should equal 9. So that means c equals 9. And so s of t equals t to the fifth plus 9, and this is in feet. Right. Another similar one down here. Driver of a vehicle at 40 miles per hour, 58.67 feet per second, brakes softly at first, then harder, coming to a stop after 7 seconds. Our velocity function is modeled by negative 1.197 t squared. We want to know how far the vehicle traveled. So now we're not asking for what the position was, we're asking for a value, right? How far. So that means we're going to be doing an indefinite or a definite integral from 0 to 7, because that's how long it was, of our velocity v of t dt. And this is our net area or net distance in those 7 seconds. So this is going to be the integral from 0 to 7, negative 1.197 t squared plus 58.67 dt. This is negative 1.197 t cubed over 3. It's the antiderivative of this. And then plus 58.67 t. This is going to get evaluated from 0 to 7. Since it's a 0, you may have noticed the trend. If you have variables in every term, 0 cancels everything. So it's negative 1.197 times 7 cubed over 3 plus 58.67 times 7. And again, at this point, it's just a calculated problem. And so this, when you punch it in, you get 273.83. This is in feet because our position should be in feet. And this is the distance it took to stop. Now this is actually a pretty accurate model. So think about this the next time you're driving and you have to slam on your brakes. If you just gave yourself a little bit more distance between you and the next car, we would be a little bit safer, all of us, right? So the last little thing in this section before we come to a close is this remark. The definite integral is a number and can be positive, negative, or 0, whereas the indefinite integral is always antiderivative. Indefinite integral is the antiderivative. So if you're ever not sure which one you're supposed to use, think about what you want from the problem, what it's asking you for. If it's asking you for a value, then you're doing a definite integral. If it's asking you for a function, you need to do an indefinite integral. And with that is the end of 4.3.